Yes.
If you have the square wave going down, do the same thing as that curve as well.
If I have the square wave going,
like, so we change the u in the direction, but if you change the, like, if the square wave is negative, it's positive.
That's a good question. If the square wave it takes a different shape, would I reach the same conclusion? Anybody wants to take a guess or informed guess? Should what?
It shouldn't be different.
It shouldn't be different. Why?
Because at the end you approximate by set of sine and sine length sine, and we didn't assume anything about the shape of the square.
Right. Actually, it shouldn't be different because in the error equation, the error equation has two parts. One part is the self-dynamics. Another one is the truncation error. The truncation error depends on if your initial condition is a square wave or a sine wave, it faces up or faces down. It depends on what the initial condition is, right? But the dynamics, which is what we are analyzing, it does not depend on the source term. If it's unstable no matter what the source term is. The source term just gives you which frequencies has a larger or smaller initial value, right? But which frequencies are stable, which are unstable, actually does not depend on what the initial condition or the source term is. Okay. All right. So this is our analysis for the forward and backward differentiation schemes. How about the central scheme? Well, let's actually use the same analysis to analyze the central scheme. So for the central scheme, our dE dt is equal to minus u times what? If you plug in the same error, the definition of the error into the central scheme, we always get that the error satisfy exactly the same scheme as whatever numerical scheme you use, plus a term that is the truncation error, right? It's the truncation error on the analytical solution. So now this is the error equation for the central difference scheme. And again, if we have E of I of any I equal to e to the j 2 pi k times I delta x, the same Fourier component, well, a as a function of t, then dEI dt is going to be the same dA dt times e to the j 2 pi k I delta x. But now what's different is the right hand side is going to be that guy. So we pull the ka out, okay? We also pull again the common component out. What's left is, well, we have I plus 1, which we have additional multiplicative factor of j2 pi k delta x, right? This times this is actually I plus 1 delta x, minus e to the 2 pi k times minus delta x, right? This times this is actually I minus 1 times delta x. Okay, so we can, in this case, simplify this a little bit further. Because we have exponential of something minus exponential of the negative of the same thing. And remember, also both of them are imaginary, right? So they have a sine and cosine component. The cosine component is a even function, so they cancel out. The sine component is an odd function, so they add up. And if I write them down, it's going to be purely imaginary because the real part cancels out. And we have twice sine of 2 pi k delta x divided by 2 delta x. Okay? So now plug this into this equation. We have dA over dt. Well, which is this component, is equal to minus u times whatever that is here, a well, this term gets this term is the same, so I'll remove both terms from both sides, right? So on the left hand side I only leave dA dt, on the right hand side I only have a times j times sine of 2 pi k delta x divided by delta x. So again, I have a purely imaginary lambda, right? So this times this is the lambda in the dA dt equal to lambda a. Purely imaginary. I have no decay, no growth. Okay. So then what explains the error when we see in the well, let's restart with the central, and what's the error we see in this? Yeah, why where's the source of this oscillation? The source of the oscillation comes from the mismatch between this and the analytical solution. So remember, the analytical solution has actually dA, let's see, analytical dt equal to minus u times a times, remember what it is, 2 pi k. Right, so if you do Fourier series and plugging the Fourier series into the analytical differential equation, you get this. So basically, we are approximating this 2 pi k by sine of 2 pi k delta x divided by delta x. And if you remember your Fourier series expansion for delta x, you know this is a very good approximation only when k times delta x is very small. Okay, it's actually approximated to second order when k delta x is very small. If you expand sine into Taylor series, you get basically x, right? And then the second term is going to be 0 because it's multiplied by minus sine of 0, and only the third term is going to be non-zero. So this is a good approximation only when k delta x is very small. And it's actually possible to draw a diagram. So if the x-axis is k delta x, okay, and here what I call it the wave number, which basically says that what is the 2 pi k, right? So here I have a 2 pi k over here, so that's the analytical, and I can also draw a sine of 2 pi k delta x over delta x, and I can see that they agree initially, but eventually I have to follow a sine curve, right? And here is when k delta x is equal to half, and here is k delta x is equal to 1, right? So basically, as my k delta x starts to approach order 1, the evolution, the oscillation frequency of that component starts to dramatically differ from the analytical oscillation frequency. In reality, what this means is that for a Fourier component, oscillation just means oscillation time is actually the same as oscillation in space, right? So basically you have a wave that travels in space. And for the analytical solution, higher frequencies travels at correspondingly a higher wave number in space, which means the speed of the travel is actually the same for different frequencies. So a straight line in the time-space frequency means a fixed speed. Okay, if you have wave, if you have a fixed speed wave, that means the frequency in time is the same, is proportional to the frequency in space. While if you look at the red curve, that means different frequencies actually travels at different speed. And you can see here that if I have a square wave, that means a square wave is composed of how many frequencies? Well, infinitely many frequencies, right? So basically, if I have all the frequency travels at the same speed, then I remain as a square wave. If different components of the square wave travels at different speed, then they physically that's called a dispersion, right? So the different components gets dispersed into different spatial locations, and the result is these oscillations we see over there, right? The very high frequencies, like these ones, they don't actually move, these basically different frequencies, they move at different speed, and the result is something like that. Okay, any questions?